Again, welcome to Precalculus course. This is Mathematics 164. This lecture will cover chapter 5, section 2 of our course textbook, and it's about log functions and their properties. So our main objective is to use and also apply the definition of log functions, and also to graph the log functions, to model the log functions, and also to use the properties of log functions, and also to use the change of base formula, which again relate to log functions. So we start with the log functions and graphs. And as we said in our previous lectures, again, plotting the graph is two steps. One, we know the input variable. Let's say we have X and Y. X is our input variable. We come up with any interval of X value, then we find the Y value. And that will be our table for the graph. Then we plot the points. Normally the points, again, is 2 dimensions. So we have each point have X and Y value. So the same concept will be applying here. Now, before we start, we'll go through the concept of, again, log functions. Here we say before the development of calculators and computers, certain arithmetic computation, such as 1.37 to the power 13, or we have 16 root 3.09, will be very difficult to perform. Calculators and again, computers make this computation more easy. So the computation could be performed relatively easily using log or logarithms, which were developed in 17th century by John Napier. Now, before calculators and computers became common in most colleges, I would say back in the 70s or early 80s, we have what we call the log books, logarithm books. And with the logarithm books, we can do this computation. So here we may express the equation x equal to a to the power y. If again, a is greater than 0 and also it's not 1, in the form of y equal to f at s by defining the log function. So we can see that again, log function and exponential function kind of goes together. Sometimes we may write this x equal to a to the power y. Remember again, y is our output variable, s is our independent variable, the input variable. But we can use this again to come up with the log functions. Sometimes also we may have log functions and we can change it to to exponential function, or we can convert exponential function to log function. And we may discuss this in the future lectures. So here we're going to focus on only the log functions. So for example, if we have a value that is positive, that is greater than 0, it's a positive, and also it's not 1, then the log function y equal to log base ax is in the log form. Now we have y equal to log base ax can be written in exponential form, and that will be the base a to the power y equal to x. So we have a to the power y equal to x in exponential form is the same as writing y equal to log base ax. So from this definition, we know that if we have a log base 381, the answer will be 4. The reason why? Because 3 to the power 4 is 81. So again, log base 381 equal to 4 because 3 to the power 4 is 81. So in this case, the log 4 is the exponent to which we have to raise the base 3 to, and we get 81. So in general, if we have y equal to log base ax, then y is the exponent to which the base a must be raised to obtain x. So y equal to log base ax is the same as saying the base a, y become exponent, so it will be a to the power y equal to x as defined here. So here we have a is called the base in both log base ax equal to y, and also base a raised to the power y equal to x. So A is always called the base. So that's why I'm calling log A, I would say log base AX. Now, why is the log in log base AX? So here we say log base AX, the answer we get is equal to Y. And the exponent in A to the power Y will give us X. So we say a log is an exponent. So the table below also shows some log equations and the equivalent exponential forms. So if I have log base 10, 100, the answer will be 2. Why? Because the base 10 raised to the power 2 will give me 100. So it will be 10 squared equal to 100. Same thing here, log base 10 is 0.1. The answer is -1. Why? Because 10 raised to the power -1, the answer is 0.1. Then log base 2x equal to y. This means 2 to the power y equal to x. Also, log base a1 equal to 0. As far as 0 is greater, a is greater than 0, it's not a negative value. So this is the same as saying a to the power 0 equal to 1. Or log base a equal to 1, because a to the power 1 is equal to a. So now let's start with the graphing and log functions. So here we have example. They say we should graph y equal to log base 2x. Again, the first step we do, come up with the tables. So I have x with this. Again, you can use any interval value, but the reason why we are using 1/8, 1/4, half, 1, 2, 4, 8, so that since this is base 2, it's more easy to get the answer. But again, you can choose any value. I can choose a value, let's say from 2 to 20 or from negative, any value you want to choose. So here we choose 1/8 because log base 2, here 1x equal to 2 to the power y. So if x is 1/8 equal to 2 to the power y, the answer will give me -3. So we can write this in the form of s, again, s equal to 2y, or y equal to log base 2x. But in the easy way, again, is to write it in this form. So s equal to 2 to the power y. I can look for any value. We start y from -3 to 3. So 2 to the power -3 will give me 1/8. When y is -2, 2 to the power -2 give me 1/4. When y is -1, 2 to the power -1 will give me half. Y is 0, 2 to the power 0 will give me 1. Y is 1, 2 to the power 1 will give me 2. Y is 2, 2 to the power 2 will give me 4, and y is 3, 2 to the power 3 will give me 8. So the best way to do this, since we know y equal to log base 2x, again, we can use the calculator to find this, but we may come to how we can find a log of any base value in the future. So the best way with the calculator, we may have natural log and also log base 10 and the calculator keys. There's a way we can also solve this, but the best way is changing y equal to log base 2x to s equal to 2 to the power y. Then we take any y value here. We decided to use -3 to +3. Then we find the value of x. Then we plot the 2 points, or the points here. So each point have 2 values, s and y. There we get the shape. So from the definition of logarithms, we can see that every logarithm has a base. Now, when we write log x, it means the base is 10. When we write natural log, ln x means natural log x. Natural log x means the base is e. So log, the base is 10. Natural log, the base is e. And these are the 2 common log keys that we normally find in our calculators. So natural log means the base is e, the log means the base is 10. So we have an example here. Let's say if $P is invested for T years at interest rate of R, compounded continuously, then the future value of the investment is given by S equal to P times E to the power RT. Again, this is a conventional formula. This is an existing formula. We don't need to prove it here. Anytime we are looking for interest or we did some investment, and the investment in this case, let's say $P is invested for T years at some interest rate, the difference is compounded continuously. We use this formula. If the interest is compounded continuously, means if I have $10 and I gain interest of $2, my new principal will be $12. So the interest you have will be added to the actual amount, and that will be the new principal. So you gain interest in your previous interest, interest in the previous interest. So it's called interest is compounded continuously. Now, simple interest means I invested $100. My interest is $2. That in $2 they will give to me. They will not add it to the principal. So in this case, to find the interest is to be just principal times rate times time. The answer you get, then you add it to the actual amount. But this means we compound it continuously. So here they said the doubling time for this investment can be found by solving for T in S equal to PERT. Now, since the goal here is to find when we will double this amount. So that will be the T. And in this case means S will be 2 times P, because P is our initial investment. S is what we get after the expiration of the term of the investment. So if we want to double it, then S equal to 2P. That means we solve for 2P equal to PE to the power RT, which is equivalent to writing 2 equal to E to the power RT, because the P's will cancel each other. So we can express this in equation in a log form to solve for the T. So again, this question, $P is invested for T years at interest rate of R. The interest rate is compounded continuously. Then the future value of the investment will be this. That's the formula. Now, the doubling time for this investment, how long it will take to double the amount, which is P. So which means S equal to 2P. We know the formula for S. So S is PE to the power RT. So we get 2P equal to PE to the power RT. So the P's will cancel each other. Then we get 2 equal to E to the power RT. So now we can express this function in the form of log. So if we remember, the base is what? E. So we get log base E 2 equal to RT. So if that is the case, to find T, it will be log base E 2 divided by R, because R is multiplied by T. When you cross the equal sign, it's going to divide. Now, this log base E is the same as writing natural log 2. So in order to find the time, we have to know the rate of the interest. So here, note that if the interest rate is 10%, we are assuming the interest rate is 10% and is compounded continuously, then the time required for the investment to double will be natural log 2 divided by 0.10. If you use your calculator, natural log 2 will give us 0.693. So roughly, we are going to say to take roughly 7 years to double the amount based on 10% interest annually. So let's try second question, graph y equal to natural log x. So the same concept, we should get a table. Now this time, natural log s is good because we can get that value from the calculator. So in this case, we can have interval value of x, let's say 0.05 all the way to 10. Or it can be any interval you wish. it should be positive values. As we can see, the asymptote doesn't go to negative. So S values will be positive. Then if I have 0.0, so what is the natural log of 0.05? I mean 0.05. The calculator will give us negative 3.0. What is the natural log of 0.10? It's given. Natural log of 10 is given. So again, natural log is a special key in our calculator. We can easily calculate it. The previous question, for example, if the log is base 2 or base 7, well, it's difficult because calculator doesn't have that key. So the best way, I'll convert the log into exponential function. Then I'll come up with y interval values. Then I'll find the x. Then I'll plot the points. Again, each point have two values, x and y. So let's say our first point here will be when s is 0.05 and y is negative 3. So it will be somewhere at the beginning. So we'll plot all the points. Now, the graph of log functions have these few properties we should know. So the equation is always y equal to log base ax. A should be greater than 1. Then s-intercept is 1 to 0. The domain always is positive res, which means x, as we can see here, s value is always positive. There's no negative. So that's why here we are saying s-intercept 1, 0. The range also will be all real values. But the all real values means the range, actually we can see from the graph here, it can be negative value, it can be positive value, but the domain is always all positive values. And the asymptote always will be y-axis. Here we say negative half. So this is the property for, again, a log, and the graph for a log function. A graph of a log function, again, the domain is always positive values or positive reals. And also the range are all real values, which can be positive and negative value. Asymptote always y vertical is y-axis. So next, let's model with log functions. So modeling concept is kind of statistics, as we said earlier, in exponential function also. Always data will be given. So when data is given, we are going to plot the data in any data analysis software. Here we can see the shape. The shape looks almost like a log function. So if I'm using Excel, I will click on the scatter. First of all, I'll enter all these values in the cells. I will select all the values, then I'll click on scatter plot, and I'll get this shape. Now, if you want to get a model, as we said earlier, right-click any of the points here and click on the trend line. When you click on the trend line on your right side, they will show us different models. We will see the linear model, exponential model, log model, polynomial model. Here we are doing, again, log model. So we click on the log and we click on show the equation, which will be the model. Then we can see the equation. So here they say we should use the technology to find the log equation that models the data. So as we explained, the first thing we need to plot the data. And when we plot the data, this is what we have. And then the application will generate this equation for us. First, we need to select a log model. Again, using Excel, we can do that. Or using a calculator like TI-89 also, it could work. We may discuss that in class if we need to do this example. So if I have the model, and now they say for the year 2000, the value of X is 100. All we need to do is to plot the value 100 into the equation, and we come up with our result. And this model is about life expectancy. So first, the data they gave us is lifespan. And the average years for the population 1920, live up to 54.1 years. By 2020, 79.5. Because in the beginning it was increasing, but now it's increasing slowly. But one thing with a log function is that a log function model, it will increase up to some stage. Then when you reach that stage, there's an increase no more. It will stay constant throughout. So we can even have a log model for how bacteria are developed, because if a bacteria is creating and we have it in a container, it will keep getting more and more, but it will reach some stage, there's no more space, the bacteria cannot grow no more, cannot produce no more. So it will reach some stage, it will stay constant. So this is our model. Now, when we use the technology to come up with a model, again, with Excel, you plot these values in the cells, select all the values, go to the graph, select scatter plot, you get this graph. Right-click any of the points and click the trend line, and that will take you to the different types of models. Here we're doing, again, logarithm. So you select logarithmic model, and it will give you this equation. So that's step one. Now, second question said the National Center for Health Statistics project the expected lifespan for people born 2000 to be 77.0. And for those born in 2010 to be 78.1. Use your model to project the lifespan for those years. So what will happen is that in my model here, we have the years X. X represents the number of years since 1900. So if it's 2000, then it will be 100, S will be 100. So what will be the year? And that's what we did here. We get 76.9. If 2010, then we are going to have 110. And when we plot 110 for X, we get 78.3. So the next question said, C said, could the expected life expand for 2015 and 2020 as given the table have been found with the model found in part A? Yes. So we can plot it and see. And when we plot, we came close to that value. So we said yes. Now the next is the properties of logarithms. Now to solve a log functions or equations, there are some rules we need to follow. And we shall go through some of them here. So in general, we say that y equal to f at x and y equal to g at x are inverse functions. They are opposite inverse functions. If whenever the pair AB satisfies y equal to f at s, the pair BA also should satisfy g at x, which means they are inverse. What the concept means here, we have s and y. Inverse of a function s and y means we are going to change the s position to y, y position to x. So if I have two functions, y equal to f at x, and the second function g equal to f at s, and I have 2 points A and B. So let's say A is my x as its value, B is my y as its value. If I plot these 2 points in y equal to f at x, and the answer is the same as if I change BA. So instead of X to be B, now X will be A, opposite. We plot it in G at X. If both of them satisfies, and that means have a same solution, then we say they are inverse to each other. Furthermore, because the values of X and Y coordinates are interchanged for inverse functions, their graphs are reflection of each other and about the line y equal to x. First, we should make sure if a is greater than 0 and a is not equal to 1, then the logarithmic function y equal to log base a x, also written as s equal to a to the power y, and the exponential function y equal to a to the power x are inverse functions. Because here you can see we are changing x and y position. A to the power y. So y is the exponent. This time we make the s as the exponent. So they will be, again, inverse. So we're going to see example. Let's say here we say logarithmic function y equal to log x. Log s means log base 10x. Is the inverse of the exponential function y equal to 10 to the power x. Because we know, again, as we said, log means the base is 10. So it will be 10 to the power x equal to y. This is the inverse, because if I'm converting y equal to log base 10x to exponential, it's supposed to be 10 to the power y equal to x. So 10 to the power y equal to x, the inverse of it will be y equal to 10 to the power x. So we say the graph of y equal to log base 10x and y equal to 10 to the power s also are reflection of each other because they are inverse functions. And some values of s and y of this function are given in table 5.4. So we have a coordinate of 1003. We can justify this by saying 3 equal to log base 10,000. And log base 10,000 will give us 3 because 10 to the power 3 is 1,000. And this is y equal to log base 10x. Now, y equal to 10 to the power x also will give us 3 and 1,000. So same thing. 10 to the power 3 is 1,000. So we can see they are inverse of each other. So here we're trying to say that y equal to log base 10x, or we can say 10 to the power x is the inverse of y equal to 10 to the power x. That's here to be 10 to the power y equal to x, and here y equal to 10 to the power s. They are inverse of each other. So this is how their graph will look like. We have y equal to log base 10x, and we have y equal to 10 to the power x exponential. And we have y equal to s, that will be the asymptote line. So this is two are reflection of each other. Now let's go through the properties of the log. The first property, we said that if a is greater than 0 and also a is not equal to 1, then log base a to the power x is the same as x. So this is for any real number x. A should be at least a value greater than 1, or a value that is not equal to 1. So it can be 0.3 anything, but it shouldn't be, it should be positive value and not 1. So log base a to the power s is x. Now to prove this result, we can use the exponential form y equal to log base a to the power x is the same as writing a to the power y equal to a to the power x, because here we can see the base a to the power y equal to a to the power x. Now, since the base are the same, a and a, they will cancel each other, then y equal to x. So this is why we say log base a to the power s is the same as x. So let's do this example using the first property of log. If we have log base 4 to the power 3, the answer will be 3. Because we're going to get 4 to the power 3 equal to 4 to the power 3. So the answer will be 3. Now the next one, we have a natural log e to the power x. Now it will be writing as log base e to the power x. So the answer also will be x. So natural log e to the power s is the same as log base e to the power ex equal to x. Now there's some second special cases for the log property. And here we say because a to the power 1 is the same as a, we can say log base a is 1. And also a to the power 0 is always 1. So log base a 1 is always 0. So these are special two cases. The base and the value is the same in one. Now, if I'm looking for log base anything, any value, let's say log base 10, 1, the answer will be 0. Log base 100, 1, the answer will be 0. Because any value raised to the power 0 is 1. So here we have y equal to a to the power log base ax. This is the same as writing log base ay, and we take log in both sides. So we get log base ay equal to log base a log as. Then they will cancel each other. So we're left with only log base ax. So in this case, I have log base ay equal to log base ax, the same base. So the answer will be y equal to x. So this tells us that a to the power log base ax, the answer is always x. And that's our second property. Second property said a to the power log base ax, the answer is always x. So let's do some two examples here. Here we have 2 log to raise to the power log base 2. So base 2 and the value is 2. So the answer will be 4. And second one, we have natural log, the exponent natural log, which is base e, x. So e raised to the power log base ex, they will cancel each other. So the answer will be x. Now the third property said, it's about multiplication. If I have log base a, m times n, we can expand this by writing log base a m plus log base a n. So log base a m plus log base a n is equal to log base m times n. So sometimes we may have a question whereby we have to expand the function, the log function. Then if it's multiplication, we expand it, addition. Now, if we want to make it smaller, we can shrink it by saying, okay, log base am plus log base an is the same as log base am times n. So let's see some example here. They say we should find the log base 2, 4 times 16. If log base 2, 4 is 2, and log base 2, 16 is 4. Well, because of these two have separate values, the first thing we're going to do, since it's multiplication, we're going to get log base 2, 4 plus log base 2, 16. We know log base 2, 4 is 2. Log base 2, 16 is 4. So the answer will be 6. We still can check it, and we should get the same answer. Now with the B, we have natural log 77. If natural log 7 is 1.9459 and natural log 11 is 2.3979. Now remember the whole concept, we have 11 and 7. So 7 times 11 is what? 77. So we can break it into 2. Natural log 77 is the same as natural log 7 times 11. So that will give me natural log 7 plus natural log 11. Now we know the value for natural log 7. We also know the value for natural log 11. So we add the two together and we have our solution. Then the next property will be division. Now division is opposite of multiplication. When we expand the multiplication, we use addition. When we are expanding the division, we use subtraction. So log base am divided by n is the same as log base am minus log base an. And let's try example here. So here we have log base 3, 9 divided by 27. So we can write this as log base 3, 9 minus log base 3, 27. Then we solve it from there. So that's what we have here. Log base 3, 9 minus log base 3, 27. Now log base 3, 9 will give us 2. Log base 3, 27 will give us 3. Why is it so? Because what value that if we raise it with the base 3 will give us 27, and that is 3. 3 to the power 3 is 27. So log base 3, 27 is 3. The 3 will be the base. What exponent that if we raise it to, we get 9? That will be 2. So 3 to the power 2 is 9. So log base 3, 9 is 2. Then we find the difference of the two. Our answer will be negative 1. And the next one, also the same concept. We have log base 10, 16 by 5. So we expand it by writing log base 10, 16 minus log base 10, 5, because it's division. Then we can use our calculator to find log base 10, 16, which gives us 1.2041. We use our calculator to find log base 10, 5, and that gives us 0.6990. So the final answer will be 0.5051. Our next property, which is exponent. So if I have log base a, m to the power n, we will bring the n in the front. So log base a, m to the power n will be n log base a, m. Again, the base always should be greater than 0 and not equal to 1. So log base a, m to the power n will be n times log base a, m. So let's see some example. Here they say we should simplify log base 3, 9 to the power 2. So the fastest way to do this is to bring the two. We can also say, okay, log base 3, 9 to the power 2 will be log base 3, 81. Yeah, we can say that, but again, here we are using the properties. So the 2 will come to the front, so we get 2 log base 3, 9. And since we know log base 3, 9, 3 to 2 will give me 9. So it will be 2 times 2. So the answer will be 4. Now it's the same as saying 9 to the power 2 is 81. So log base 3, 81. What value if I raise it exponent? And 3 to what exponent will give me 81? It's 4. 3 to the power 4 will give me 81. So again, we can solve it either using this property or just straightforward. So let's see the B. We have natural log 8 to the power negative 4. This is more better for us to use this power rule. So it's better to do it negative 4 natural log 8, because natural log 8, we can easily find it in the calculator. So whatever value we get, 2.0794, we multiply by negative 4, and that will give us our final solution. So next, we're going to do the change of base. There's a special formula we use here. The whole concept is we can see, for example, here we have y equal to log base bx in the form of b to the power y equal to x. Now, if we take the base a, log of both sides, we have what is written here. Log base a b to the power y equal to log base a x. And here we can find the y, which will give us log base a x over log base a b. Now, to give us the whole idea, let's see the rule here first. If we have a value that is not equal to 1, and also the b value not equal to 1, a should be greater than 0. Also, the same thing, b should be greater than 0, because those are the bases. So here we say, for example, log base bx equal to log base a x over log base ab. Log base bx is the same as saying, so here we take a log a and we use the x and b. So the first value x. So a good example, let's say we are looking for, again, we're going to solve an example in a few seconds. So let's look the next rule here. So if we are using base e, log base bx equal to natural log s over natural log b. Or if it's base 10, then we say log s over log b. So actually, this is the example I want to say. I know the calculator can give us the value for base 10 and also natural log. So if I have equation that I have log base b x. B can be any value, x can be anything. Let's say log base 720. Log base 720 is difficult to find it from the calculator. Log base 720. So what I will do, I will just use natural log 20. Again, the base is 7. So natural log 20 over natural log 7. So I can use the calculator to find, or I can use the base 10. Normally, whatever the problem is, we can convert it to either natural log or log base 10. The reason why, because of the calculator. So the best way to do this is a good example here. We have log base 750. Well, it's difficult to look for this solution in the calculator. So we use what we call the change of base formula. I can use either natural log or base 10 because those two, again, are in the calculator. So log base 715 is the same as writing. And here we decided to use natural log, same as writing natural log 15 divided by natural log 7. So you get the calculator, we put both values, and we get our final solution. We can also check the calculator, see if it works. 7 to the power 1.39166 in exponential form, it should be equal to 50. Because we are changing this log base 715 to exponential form. In the exponential form, the answer we get here will be our exponent for 7. Then it should equal to 50. So again, that will be the conclusion for our lectures on log functions. But before we go, again, this example, we use the natural log. Same thing, we can use the log base 10. So here we can say log base 15 divided by log base 7. It should give you the same answer. Either use the base 10 or the natural log. So again, wish everybody the best. If you have any question, post it in the Blackboard, or you can send an email. See you in the next class lectures. Thank you.